Good morning, welcome, and thank you for joining us for this webinar on PTV Vissim. My name is Axel Leonard and I'm responsible for Vissim product management and services at PTV. Next to me is my colleague Sven Beller, who will answer questions you may submit via the chat functionality during and after the webinar. The webinar is scheduled to take about 30 minutes. And we will start with some basics about Vissim, then we will take a look at the Vissim graphical user interface. We will also discuss Vissim's behavior models and what type of results one can get out of Vissim and what interfaces the software provides. And to conclude, I will provide some additional information around the software, and there will be also additional time for questions. The PTV Vision suite includes software for different modeling tasks and analysis levels. For the strategic transport planning and forecasting, we have Visum, and we have Vistro for smaller scale traffic impact analysis and signal optimization projects. For real-time traffic management, we have Optima for traffic state estimation, short-term prediction, and real-time scenario testing, and Balance for network-wide signal optimization. Vissim is a multimodal simulation software tool for operational level analysis. VisWalk is the pedestrian simulation software, which is available as part of Vissim or as a standalone tool. The following animation, which was exported straight from a Vissim simulation, shows several important aspects of Vissim. You can see that traffic is represented by individual vehicles rather than a macroscopic representation. Each individual behaves according to behavior algorithms, and you can see it is multimodal. There are different types of motorized vehicles, such as passenger cars and trucks, public transport vehicles, as well as cyclists and pedestrians. And clearly they all behave differently, and which is taken care of by different behavior models and parameters sets. And the different modes do not only coexist in the simulation, but they also interact, which makes the simulation truly multimodal. The network is represented by basic elements, links and connectors, and areas for pedestrians. These elements are flexible such that virtually any type of network can be modeled. Traffic control, traffic management, and conflict handling is an extremely important part of a traffic simulation, since congestion is mainly induced at intersections, junctions, or merges. And Vissim allows the implementation of various sorts of traffic signal and traffic management control algorithms, as well as different mechanics for conflict treatment. Furthermore, there's furniture, such as buildings and trees. These are mainly used to make the scenery look more realistic, which can be very important if the simulation is presented to a non-technical audience. And of course, the animation is only one output of a simulation, and in most cases not the most important one. Vissim allows reporting various measures of effectiveness, such as travel time, queue length, volumes, or total time spent in the system. So let's have a look at Vissim's graphical user interface. It contains multiple windows, toolbars to edit and analyze the model. These are network windows, where the networks are edited and where you can view the network objects and simulations in 2D and 3D. The available views can be viewed, selected, and edited in a smart map, shown down here to the left. And here on the left side, you can also find the network object toolbar, where you can control what objects can be created and edited, as well as the visual appearance and the visibility of network objects. Just to demonstrate how a Vissim model is created, I will draw some links here. So here's the first one with some curvature. I will add another lane to the right, and I will create another link. To feed in vehicles, I will create some vehicle inputs for this link, and for this link. And finally, I will determine the right-of-way at this intersection here by the use of a conflict area. Okay, and now I let the simulation run. Okay, I forgot something. I created vehicle inputs, but I didn't put any volumes in there, so I will do that in this list down here. I restart the simulation. You can see the vehicles running. The network editor supports efficient network editing, for example, with the duplicate functionality, which allows to duplicate existing objects, such as this link here. You can multi-select and multi-edit all objects. You can select them in the network editor and edit them in the quick view window shown down here. For example, I will now change the gradient of the selected links to be 2. All objects can also be edited in lists. For example, in this link list shown down here at the bottom, lists give access to all attributes of all objects in Vissim, and they are equipped with some nice functionality that will help you to review and edit data efficiently. Lists can be synchronized with network editors, so I can select if I want to pan or to zoom to objects selected in the list. And other functionality in list is as you would expect, including sorting with respect to selected attributes, and also multi-select and multi-edit of attributes, and copy and paste functionality, so you can directly transfer data between Vissim and other tools like Excel. That's easily possible with lists. Network objects can be assigned to levels, and levels are managed in the levels sidebar. So levels can be locked to prevent editing and made invisible, just as you know it from AutoCAD-like design tools. And next to the level sidebar, there's the background image sidebar, where you can control the visibility of individual background images. All windows that you can see here in the graphical user interface can be opened and hidden as needed, and they can also be arranged as needed, and these layouts that you can create can also be saved and called later on. Now we will take a look at the behavior models used in Vissim. For the vehicles to move, there are models needed for the different levels of the driving task. On a strategic level, there's route choice to tell the vehicles on what route to get from A to B. On a tactical level, vehicles have to decide what lane to select based on their own route and the planned routes of other drivers. On an operational level, vehicles have to actually accelerate and decelerate based on car following rules, and they have to change lanes based on the situation on their own and other lanes. And in conflict situations, vehicles in minor traffic streams have to decide whether to give way or to use an available gap in the major stream. And of course, behavior is not the same for all vehicles in the network, but vehicle type and vehicle class specific. One way to model vehicle routes is the use of static routes. In this case, routes with fixed, time-dependent, user-defined proportions are defined at decision points. And this makes sense if the route choice is known from field observations, an estimation process, or a strategic model. Demand provided in origin-destination matrices can be assigned to the network based on a dynamic stochastic user equilibrium assumption. And in this case, simulation is repeated until the OD flows are distributed according to the stochastic user equilibrium. And this is checked in every iteration against user-defined convergence criteria. Finally, there is vehicle rerouting, emulating dynamic in-vehicle navigation systems. And here, vehicle recalculate the optimal route to the destination during the trip. And if all vehicles are repeatedly rerouted, this results in a one-shot assignment. And what method to use actually depends on the size of the network, the available data, and last but not least, on the objective of the study. If vehicles travel along their routes, they continuously have to decide which lane to use. That is the lane selection process, and they eventually have to change the lane to get to their target lane. In lane selection, the vehicle applies a defined and location-specific look-ahead distance to assess which of the lanes are the best for them. For example, in a situation shown up here, the driver decides upstream which of the two possible lanes at the first turn can be used further downstream. And of course, the look-ahead distance is user-definable. If there's free lane selection, the vehicle also compares its own speed with its desired speed and the speed of the neighboring lanes to check whether another lane is more attractive. And another level of lane selection happens if there's cooperation between drivers. Drivers may change the lane not only to optimize the situation for themselves, but also to let other vehicles merge in. As you can see here, we have 2 times the same situation without cooperation at the top and with cooperation at the bottom. And as you can see, with cooperation, the driver on the main carriageway moves to the middle lane to let the driver merge in from the on-ramp. For the lane change process itself, the driver checks if there's available gaps and if it is possible to change the lane without impacting other drivers. Yet the drivers accept a certain impact to other drivers depending on their own aggressiveness. So we check the performance of a freeway merging situation as predicted by Vissim with an example from the highway capacity manual. Basically in this situation, vehicles drive from left to the right, and some of them have to merge from the on-ramp to the main carriageway and vice versa. And as you can see, the performance predicted by Vissim is very similar to what was documented in the HCM. And what is documented in the HCM should be based on empirical findings. So for the vehicles on the main carriageway as well as for the merging vehicles, in these diagrams you can see the average speed on the y-axis for the vehicles on the main carriageway and the merging vehicles for different parameter sets. And the rightmost column represents the simulation results gathered with enhanced driver cooperation, and the red line here represents the results published in the HCM, and as you can see, it matches pretty well with the Vissim simulation results. In some cases, vehicles share lanes in that they arrange themselves next to each other within one lane or by ignoring existing lane markings. One example is road traffic under heterogeneous conditions. Here you can see an example with different types of vehicles arranging themselves, ignoring lane markings and simply utilizing the available space. Another example are cyclists. Down here you can see cyclists passing a bottleneck with different driving behavior parameters resulting in different capacities. The principle behind the lateral movement is that the vehicles try to find the lateral position that maximizes the longitudinal time to collision while keeping a speed-dependent and vehicle type-specific lateral safety distance. And we expect that these applications become more and more important and that it is important to be able to model them realistically. And just to make the overview complete, I want to mention that there is a special movement model for pedestrians implemented in Vissim and Viswalk called the social forces model. Here, pedestrians try to reach their destination as quickly as possible using the available area, trying to avoid collisions with other pedestrians and obstacles. This will be discussed in detail in a dedicated VisWalk webinar, which is coming up in the next week. Of course, different modes of transport can share infrastructures, so the interaction of vehicles, cyclists, and pedestrians have to be modeled as well. This is an example that shows an intersection in Strasbourg in France with pedestrians, cyclists, motorized vehicles, and public transport vehicles. And Vissim was used here in this project to assess different geometry layouts and different traffic signal control programs at these intersections regarding the delays for the different transport modes. Traffic signals are a very important part of the road transport systems, and they determine operations to a large extent. And hence, they have to be simulated in a realistic way, as realistic as possible for the simulation to be relevant. There are various ways to simulate traffic signals in Vissim. Fixed time controllers can be modeled based on signal groups or based on stages. If you want to develop an actuated signal controller logic, you can use Vissim's own vehicle actuation programming language, VAP, or its visual front end, VisWap. And you can also link external controllers to Vissim to simulate real controllers in the loop or to develop and test customized external controllers. Some more details about VisWap. VisWap allows flowchart-based programming of actuated control logics, which has the advantage that the signal logic is straightforward to read and write, also for people who are not proficient in software programming. And through VisWap, you have access to detector data, and you can set the signal states to simulate any type of vehicle actuated signal programs, including public transport preemption. In this example down here, you can see the simulation of a roundabout with the tram line running through its middle and actuated signals to allow the tram to pass without having to stop. We'll now look at what Vissim can produce in terms of simulation output and how Vissim can interface with other tools. Vissim simulation results can be stored as animation files, video files, as raw numerical data, and aggregated numerical output. Animation files basically allow replaying a simulation at any time after the simulation, providing the exact same appearance as the original simulation. For example, to present the simulation to a client. Videos have the advantage that they can be replayed without having Vissim installed, just by using any media player. Aggregated results and raw data include a wide range of performance indicators and traffic-related data. Examples for aggregated results are queue length, node and turn delays, local detector data such as speed, occupancy, and volumes, and network-wide performance measures such as the total time spent in the system. Raw data, for example, can be individual vehicle trajectories or protocols of lane changes. Aggregated results can be accessed in lists. You can access results of individual simulation runs, like shown here. We have 3 time intervals and 3 simulation runs. And for each of them, we have network performance results like average delay, average number of stops, and average speed per vehicle, as well as the total time spent in the system. And performing multiple simulation runs for one scenario is what you typically have to do because microscopic simulation in Vissim is stochastic and not deterministic. Many decisions and properties of vehicle driver units in Vissim are drawn from distributions rather than just using a deterministic variable. And this is done to reflect stochasticity observed in the real world. For example, there's normally not one single driver entering the system at the exact same time with the exact same desired speed every day. And the consequence for the modeler is that he has to conduct multiple simulation runs per scenario to acknowledge for this stochasticity. Vissim supports this in that it stores results of multiple simulation runs and in that it calculates aggregated results and some basic statistics over multiple simulation runs, as shown here. For all the performance indicators, there's the average, minimum, maximum, and standard deviation calculated and shown in this list. Lists can not only be analyzed in Vissim, but also exported to text files and to databases for further processing. Results can also be used to color code network objects in Vissim, like in this example here. Here the link segments are color coded based on the average speed. And this can be displayed during the simulation and after the simulation for any time interval in simulation run, as well as for aggregates over time intervals and simulation runs. Although Vissim allows to do a lot of things in terms of editing, analysis, and visualization, we think it is very important to provide an open system such that the user can pre-process or post-process simulation data and that he can control the simulation while it is running. On the input side, it is worth mentioning that there are two open XML file formats to prepare data for Vissim. The actual input file format, INPX, with detailed descriptions of network objects, and the more abstract network description format, ANM, which is also used for data exchange between Visum, Vistro, and Vissim. And besides that, there are some dedicated importers for Synchro networks, AutoCAD files, and Google SketchUp models. To control the simulation while it is running, there are also multiple options. The COM interface gives access to all attributes of all objects from outside Vissim. So using virtually any programming or script language like Python, Visual Basic, or C++, you can customize your Vissim model. For example, you can implement your own active traffic management systems or route choice models. And besides the COM interface, which is the generic interface, there are several specialized DLL interfaces that provide an even lower level access to Vissim data, such as the driver model DLL, to implement customized car following and lane change models, the signal control DLL to implement new or link external signal control algorithms to Vissim, and the driving simulator interface. On the output side, I already mentioned how you can get simulation results out of Vissim, and there are various tools around that have importers for Vissim output to enable further processing, such as 3ds Max for professional 3D visualization, and Weaver for emission modeling, and SSAM for safety analysis. We now look at some example in which some of these interfaces were used. So virtually any active traffic management system or ITS can be modeled with web and COM in Vissim. Ramp metering is a very obvious one because it is nothing else than a traffic signal operated with any of the signal controllers I mentioned earlier. Decision algorithms for managed lanes, pricing, and route choice can be modeled with a COM interface to analyze the effect on the system performance and also on the revenue you can generate. And algorithms for variable speed control and temporary use of hard shoulder lanes can be modeled with web and COM, through which also the underlying behavior, in this case choice of lane and desired speed, can be controlled. And of course, many more types of intelligent transport systems can be and have been simulated with Vissim, including applications that use car-to-car or car-to-infrastructure communication. This example shows a rather futuristic transport system called Personal Rapid Transit, PRT. The trips of the vehicles shown here are controlled from a central unit that takes into account the current position, occupancy, and destination of the vehicles, as well as the current demand at the stations. And I mean, whether such systems will be deployed in the future in larger scales, we do not know that. Yet it is useful to have a simulation tool ready that is able to simulate those envisioned transport systems, for example like this or other forms of autonomous vehicles, because simulation allows to assess the impact these systems have on the overall transport system prior to their implementation. So this concludes the introduction to Vissim, and we will now provide some further information related to the software. Of course, you can continue to submit questions via the chat. This was an introductory webinar, and we have more webinars coming up, which will be more specific and more technical. Topics are pedestrian simulation with Viswalk, simulation of public transport simulation, public transport systems in Vissim, emission modeling with Vissim and NViver, and simulation of active traffic management. In addition to these webinars focusing on the microscopic simulation, there are also various webinars offered on strategic planning applications with Vissim. And for those who want to learn the software in detail and hands-on, we offer training courses on different levels. There's a 2-day introductory course on Vissim, and there are 2 advanced level courses, one focusing on modeling actuated signal control with SWAP, and the other focusing on the use of the COM interface to customize the simulation. And for pedestrian simulation with Viswalk, there's also a 1-day introductory level course available. Dates and locations for these courses can be found on our website, where you can also directly register. And in addition to the standard classroom training, we offer individual training and training on the job on request. Further information can be found on our website. Here you'll find descriptions about Vissim and our other products, training courses, and an FAQ section. And you can also get trial versions of the software tools and inquire for further information. There's also a YouTube channel with many Vissim and Viswalk examples provided by our users. So if you want to see more use cases, it is always a good idea to visit this YouTube channel. And there is a Vissim LinkedIn forum where more than 1,000 Vissim users share their ideas and expertise. So this concludes the webinar. We will be around in the chat for another couple of minutes to answer your questions. So thank you all for attending this webinar on PTV Vissim.